Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Okay, I will continue. This is series number 2, episode number 2. Okay, this is the second video continuing the previous video. We have actually discuss frame with side sway, the concept. So I want to continue the video. Okay, considering the same frame. Okay, the same frame that we have discussed previously. So we will continue to solve the the member and moment, using a moment distribution method. So remember that in moment distribution method we will analyze member and moment, or it is also known as internal moment, at each end, in beam and in frame. But we are focusing now on frame analysis, frame with side sway analysis. So in screen right now, this is actually a frame, the diagram of frame, which actually follow the principle of superposition. So as I mentioned in my previous video, why we need to use the principle of superposition? Because we need to analyze FEM separately, between unknown, between external loading and side sway delta. Okay, we cannot combine FEM due to external loading and delta together. We have to separate external loading and delta. Okay, we will analyze fixed end moment, okay, using external loading in one table, that is table number 1, and we will analyze side sway frame. Using another table. So means table number 2. Okay, table number 2. So this actually will fulfill principle of superposition. So in the diagram, so we can see that, we have a diagram. I have label as label number 1, label number 2, label number 3. Okay, label number 1 is actually the question given, where in the frame there are external loading considering 200 kilonewton, which is located at B in right direction, and then we can see that there is a 35 kilonewton per meter UDL, UDL subjected along member BC, and due to unsymmetrical condition of the frame, due to unsymmetrical loading, due to unsymmetrical geometry of the frame has both, external loading and delta. And in order to analyze, table number 1, we have to remove delta. So when we remove delta, what we do is we have to put an artificial support at C. We have to have the properly restrained frame. We have to have properly restrained frame, so that we actually remove the delta. Then we can focus the analysis, the frame analysis, considering only external loading. So that is for table number 1. It means that table number 1 will be focusing on frame number 2. Frame number 2. So, and in frame number 2, there is a restraining force which comes with an artificial support, pin support at C. So this restraining force R, we have to neutralize. We have to neutralize with, this is actually plus, with a side sway frame. We have to have another frame which is subjected, to R only. Okay, so this side waveframe okay, has only delta, no external loading, no FEM due to external loading. So but for diagram number 3, actually this is not representing table number 2. Table number 1 represent by diagram number 2, because FEM for table number 1 can be calculated using W, which is given in the question. Table number 1, okay, will be using, okay, diagram number 2, because FEM due to external loading, we can calculate the value. We can calculate the value of FEM for member BC, because we know that W is 35 kilonewton per meter. That is for table number 1. But for table number 2, we cannot directly use diagram number 3. We cannot calculate FEM due to delta, because we do not know delta value. So when we do not know the delta value, we cannot use direct method. We cannot calculate FEM due to delta. We cannot calculate it because we do not know the delta value, and we, of course, this is the real one. We cannot assume delta value here, and we do not need to calculate the delta value. So what we will do in table number 2, because we have to analyze this question using two table. We have table number 1 for non-size waveframe, and we will have table number 2 for size waveframe. So for non waveframe, table number 1, considering diagram number 2, it is direct. Okay, direct means we can calculate FEM using the value that is given in the question. But for table number 2, we use indirect method. Okay, we use indirect because we do not know delta value. When delta is known value, when delta is given, then only we can calculate FEM using delta. That is direct one. But in this case, diagram number 3, table number 2, we cannot calculate FEM because we do not know the delta value. So what we actually do is we use indirect method. Okay, indirectly we analyze this frame. Indirectly we analyze this frame, but not this one. Another diagram. So we should have the fourth diagram, which is actually proportional with diagram number 3. Okay, diagram number 3. So that one we can assume. Okay, we can assume the FEM in the diagram. Okay, but of course we have to consider certain condition. So we have to have another diagram. Okay, called as, okay, diagram D. Okay, called as diagram D. So we have like this. Okay. Okay, so okay, this is diagram number 4. Okay, so we introduce R prime. We introduce R prime. Okay, diagram number 4. Okay, is proportional with diagram number 3. Okay, we introduce diagram number 4, which is proportional with diagram number 3. But diagram number 4, okay, we use diagram number 4 for table number 2. We use diagram number 4 for table number 2. Remember that we have two tables. The first table is for non-sway frame. The second table is for side sway frame. In side sway frame analysis, we have two tables. Table number 1 is to analyze non-sway frame. Okay, and table number 2 is to analyze side sway frame. Table number 1 is to analyze external loading only. So the FEM in the table, we calculate based on external loading. And for table number 2, we focus on side sway frame. Side sway frame. Okay, so in order to do that, for table number 2, for side sway frame, since delta is unknown, we cannot use diagram number 3 directly, so we use indirectly. Okay, indirectly, we introduce another frame which is proportional with diagram number 3, but this frame is subjected to R prime. It is actually the same frame, so if in diagram number 3, there is an R, okay, R. So in diagram number 4, okay, it is subjected to R prime. If in diagram number 3, due to R prime, there is a side sway, okay, there is a delta. So here also, diagram number 4 also has delta, we label as delta prime. It is proportional, okay. So if in this diagram, let's say, okay, this is the delta. Okay, this is the delta. Okay, so delta. Okay, due to R prime, okay, there is delta at B and C. It is equal delta. So this is delta. This is also delta. Okay, so in diagram number 4, due to R prime, so there will be delta prime. Delta prime. Okay, like this. Okay, so for frame analysis, we have to focus on horizontal displacement. It is side sway. Okay, move. Okay, side movement. Okay, it can also move to left direction. Okay, depending on the loading, and if we do not, we do not sure which direction the frame deflect or move, we can assume, okay, the frame is tend to move to right direction. Okay, if we do not sure, but if we have the problem, the frame, where from the loading we know that the frame is tend to sway to left direction, so we have to consider it as left direction. So of course there is a difference when we assume the frame is tend to sway to right direction and left direction. Okay, because FEM itself reflect the behavior. FEM itself reflect the behavior. FEM due to loading, when we calculate FEM, the moment direction reflect the reaction at the end. at the end point. Okay, at the end point to counter back the bend beam to its original position. So in side sway frame, okay, due to delta, the column uh, move to right or left direction. Of course, it shows behavior. Okay, movement is behavior. So the fixed end moment. Okay, when we apply fixed end moment, the function of fixed end moment actually to push back. Okay, to push back the frame. Okay, to go back or to move back to its original position. Okay, so the moment we apply in that direction. Okay, in that direction, so that when frame is tend to sway to right direction, so we have to apply moment counter back. Okay, so that it will bring back. Okay, the moment will bring back to its original position, which is straight position. Okay, so we have here. Okay, due to r prime we have delta prime. Due to r prime we have delta prime. And remember, in diagram number 3, okay, the end moment, as I mentioned in my previous video, in diagram number 3, the end moment r restraining force and delta, okay, bring end moment in diagram number 3, and the label is m. The label is m. The label is m. Okay, the label for this one is m naught. Okay, for diagram number 2, table number 1, the end moment we label as m naught. We label as m naught. Diagram number 3, okay, due to r and due to delta, okay, the end moment, okay, will occur, okay, at each end, and we label end moment in diagram number 3, which we do not know the delta value, okay, and we also do not know the r value. So m is unknown. In this case, m is unknown. So this m is unknown value. Okay, this m is unknown value. We label as m. Okay, we cannot calculate m using in the table. We cannot calculate m in the table because we do not know the delta value. Because FEM, the formula to calculate FEM due to side sway, due to delta, we must know delta value. When we do not know the delta value, we cannot calculate m directly. But indirectly we can by introducing another frame which is proportional with diagram number 3. Okay, so in diagram number 4, okay, in diagram number 4, okay, in diagram number 4 we have the same frame, but this is subjected to r prime, and due to r prime there is a delta prime which is located at two position B and C, which has same, okay, equal value, and due to r prime and due to delta prime, okay, it actually bring the end moment at each end. End means end of each member, okay, at each end. So this end moment in diagram number 4, due to r prime and due to delta prime, we label the end moment as m prime. We label the moment as m prime. Okay, this is m prime. We label this as m prime. Okay, so remember this equation. Okay, this equation m total is actually the total moment considering both external loading and side sway, both external loading and delta. Okay, so it is m naught plus m based on the principle of superposition. Okay, in this equation, m naught we get from table number 1. Okay, but m we cannot get it directly from table number 2. Okay, m is remain as unknown. That is why we introduce another diagram number 4. Okay, because m is unknown, so we have two diagram. Okay, diagram number 3 and diagram number 4. Diagram number 3 and diagram number 4. Okay, so it is just like this. Okay, it is just like we do uh, okay, interpolation between two triangular. It is just like that. For example, if we have this, okay, it is just like, okay, we can get the relation between m prime, okay, that we get from diagram number 3 and diagram number 4. Okay, it is actually interpolation process that we can get from two table. Okay, that we can get from two table. For example, if we have two table, so this interpolation concept actually everybody have learned this, okay, in school, in secondary school. Okay, okay, doesn't matter, move like this. Okay, diagram number 3 and diagram number 4. Okay, we try to understand the relationship between those diagram by considering this triangular. Okay, by considering this triangular. So we have these two triangular, okay, where the first triangular representing frame diagram number 3, where in the frame there are r value and m value, r and m we get from frame diagram number 3. And in the second triangular, okay, second triangular represent frame in diagram number 4. Okay, which in the frame there are r prime and m prime. So using interpolation, okay, this is actually table number 2. Table number 2 representing frame, table number 2. In table number 2, what we can get, okay, is actually m prime value, which we can get from table 2. And from the table, we can calculate prime, r prime. Okay, in diagram number 3, we do not know the value of m. This is unknown. Okay, but we can get r value from table 1, because from uh, from this diagram, table number 2, when we analyze table number 1, we calculate FEM due to external loading, due to 35 kilonewton per meter. Okay, when we analyze this, we can actually determine r value. Okay, from table number 1, we can get r value, and the r value that we can calculate from table 1 will be using in diagram number 3, because it is equal but in opposite direction. Okay, means that we can have r value from the triangular, from the triangular representing diagram frame diagram number 3. Okay, so having this two triangular, okay, having these two triangular, if we can have relationship, okay, we can write relationship, okay, based on interpolation process or interpolation method. Okay, so it is between r and m and r prime as well as m prime. So the relationship between this can be written as this. Okay, it is m over r, which is equal to which is equal to m prime over r prime. So what we want is m. So we rearrange back this. So we will get m, which is equal to, we group r together, r divided by r prime, okay, times with m prime. Okay, times with m prime. So we have this. Okay, we have m, which is equal to r divided by r prime times m prime. Okay, this m we can substitute into the principle of superposition, where we we have derived in the first place m final or m total. Okay, m total from diagram number 1, m total is equal to m naught plus m. M is unknown. Now we have actually established the equation, okay, for m, okay, from interpolation process, okay, from interpolation between two diagram number 3 and diagram number 4. So we substitute after after we have do interpolation, we can substitute m, which is equal to r over r prime times m prime into this equation. So we can rewrite the final equation to calculate the final n moment or the total n moment, considering both effect, external loading plus delta. So by this equation, so we have m total equal to m naught plus r divided by r prime times m prime times m prime. Okay, times m prime. So in summary, okay, m naught, okay, this is for table 1, this is for table 2. Okay, r from table 1, r prime from table 2. Okay, so we can summarize the process to analyze, okay, analyze frame with sidesway by this step. Okay, step number 1, okay, summary of procedure. Okay, we have step number 1. Okay, we have step number 1. We, of course, in moment distribution method, the first important thing to solve is to calculate distribution factor. Okay, we calculate distribution factor from stiffness factor. Distribution factor is equal to member stiffness factor divided by joint stiffness factor. Okay, and we will use distribution factor in order to distribute moment, okay, in the table. So we have to calculate K as well as DF. Okay, that is the first step. Okay, the second step. Okay, the second step is I divide. Okay, the second step is focusing on the first table, which is non-sway frame analysis. non-sway frame. And in this in table number one, non-sway frame, this is actually for table number one. So for non-sway frame, okay, I can divide into three step. Okay, okay, we have to calculate FEM due to external loading. So due to external loading, FEM. And as I always mention, FEM is actually member and moment. The first member and moment in the table. Okay. And then second step is distribution table. Distribution table. We distribute distribution table in order to calculate. Okay. In order to calculate. Okay. I write like this. We want to calculate n moment. We have to calculate n moment. This is member n moment. And moment, the symbol is M naught. The symbol is M naught. We get this from distribution table. This is from table number one, distribution table. And the moment that we distribute, okay, the moment that we distribute is based on fixed end moment. Okay, fixed end moment. In the table, we have to distribute moment, and we have to carry over the moment. Okay, there are two main steps in the table. We have to distribute moment, we have to carry over the moment. Okay, and C after having n moment, okay, n moment, then we need to calculate R, restraining force, restraining force R. Okay, we calculate this R using static equilibrium. Okay, using static equilibrium. Equilibrium. Okay, this is actually the second step. Okay, but this is the first table. Okay, the first table. So representing this, okay, we have frame. We have this frame. We have to analyze this frame. So this is for table number. Okay, this is for. Okay, this is for table number one. Okay, this is for table number one. Okay, this is for table number one. Okay, this is the frame that we are going to analyze for table number one. Okay, from this frame, we will get M naught, and in order to calculate R, restraining force, we have to complete the free body diagram for this frame by putting, okay, all the reaction at the support. Okay, all the reaction at the support. Okay. Okay, this is fixed. And then horizontal reaction. Horizontal reaction. Okay. Okay. For the horizontal reaction, we can put in any direction, doesn't matter. Okay. I have chosen, okay, this direction for AX and DX. AX and DX. So this is AX. This is dx, this is dy, this is ay. Okay, and then the moment at fixed, the moment. Okay, the moment. So this is m a, this is m d. Okay, this will be the diagram we use to analyze, okay, analyze end moment and restraining force R. Okay, and this is for the first table, the first table. Okay, so to analyze this, okay, I will move this to, this is static equilibrium. Okay, this is properly restrained frame. This is for table number 1. We have removed delta here from here. Okay, this is, okay, properly restrained frame. So copy this first. Okay, because I will continue to calculate the end moment using Excel. So I move the diagram to Excel. Okay, because we can actually calculate the end moment. We can actually calculate the end moment using Excel. Okay, wait. I need to reduce this. Okay. Okay, this is the frame that we are going to analyze for table number 1. For table number 1, I reduce a little bit. Okay, so for table number 1, we will calculate end moment, and the label for end moment is M naught. M naught. So we have here 3 members. 3 members means we have 6 end moment because one member has 2 end. Member end moment represent end, representing moment at each end. Okay, one member has 2 end. It is just like one element has 2 node. Okay, it is just like one element has 2 node. So one member has 2 end. And so it is actually represent member and moment. Okay, the member and moment. Okay, so we have 6 member and moment because we have 6 end. Okay, one member has 2 end, so there are 6. So we have, okay, we have AB, we have AB. Okay, we need to save it first. Okay, save. Okay. Okay, wait, reopen again. Where is it? Book 1. Okay, this is the Excel file. Okay, so we have AB and then BA. Okay, this is for member number 1 and number 1 and number 2. Okay, we have member number 2. We have BC and CB and CB. So BC is N number 1 for member BC. CB is N number 2. Okay, for member BC. And we have CD as well as DC. Okay, this is the member. six member six member n. Okay, six member n. So we are going to analyze member n moment, six member n moment. Okay, we have to calculate K first, stiffness factor. So I want to calculate stiffness factor in the table using table directly. Using table directly. So it is K. And of course, it is in terms of EI. And EI, I have set constant. Okay. And actually, in order to calculate this distribution factor, the EI will be cancelled. Okay. So by looking at the diagram, okay, since okay, we have n fixed at A, n fixed at D, and internal support, okay, or rigid joint. So all member we can use 4EI over L for the formula. So it is 4 divided by 7 for member number 1 or member AB. Okay, and actually AB and BA is the same thing. Okay, it is the same thing. Okay, for member BC, we use 4 divided by 5 because the length is 5. Okay, and then for CD, it is also 5 and we use 4 over 5, so it is also same. Okay, if we have here EI is not constant, then we need to consider. Now all EI is constant. Okay, so this is EI, means that K is 0.571 EI, KAB is 0.571 EI, KBC is 0.8 EI, KCD is 0.8 EI. So next after that is distribution factor. Distribution factor. So to calculate distribution factor, okay, for n fixed is 0 distribution factor. Okay, and fixed is 0 distribution factor, and pin is 1 distribution factor, and at each joint total must be 1. Okay, total must be 1, means that if we have BA and BC, so total must be 1. If we have BA, BC, BD, total also must be 1. So distribution factor for BA, it is 0.571 divided by 0.571, okay, plus with 0.8. Okay, we get 0.417. Okay, 0.417. So actually for BC, the FBC, it is 0.8 divided by total 0.571 plus 0.8. Okay, but okay, we can calculate it easily using this 1 minus 0.417, because the total, okay, the total distribution factor at joint or at rigid joint is 1. Okay, so for CB and CD, so we will get 0.5, 0.5, because the value is equal. Okay, so these are the distribution factor. So we will use this to calculate moment, to calculate member and moment. Okay, so after distribution factor, remember the first member and moment in the table is come from fixed end moment. So the first thing to do is to put the fixed end moment, and by looking at the diagram, fixed end moment, remember fixed end moment, we calculate fixed end moment in order to distribute the moment to the joint. Okay, so that is why FEM, we only have the value for member BC. Okay, we have value for member BC only. We don't have we don't have FEM for AB. We don't have FEM for CD. Okay, we only have FEM for member BC because as I said previously, okay, FEM it is just like equivalent nodal forces where we need to distribute to the nodes. Okay, distribute the force to the nodes. Okay, so for member BC, so it is WL squared over 12. Okay, I believe everyone have remember the formula, and we have to put negative, okay, representing behavior. Okay, I have explained about FEM in last three videos. Okay, the concept of FEM. Okay, so it is one negative, one positive because of the behavior. So we have to calculate the value. Okay, it is negative value first. It is W is 35 times with L is 5 times another L squared. Okay, divide by 12. WS squared over 12. So we get the answer as negative 72.917. Okay, so for CB of course we will have the same value, but the sign is positive. It is positive because of the behavior. Okay, we get this one negative, okay, representing FEM at, okay, at B, and FEM at C is equal to positive 72.917. Okay, so FEM is the first member and moment in the table. Okay, we use the table to calculate member and moment. And okay, one thing important is the first thing to do in the table is to distribute moment. And the moment that we distribute is not member and moment, but it is joint moment. Joint moment is opposite with member and moment. I have explained in my previous video. Okay, I have actually prepared this semester three of four. Okay, this is video number 5 to explain about frame. Five video for frame. Okay, for frame I have made 5 video including this, and I have repeat okay, repeat telling you that in the table, what we distribute is not member and moment, but we distribute joint moment. And joint moment is opposite. Joint moment is opposite with member and moment. That is why we need to change sign. Because the one that we distribute is not member and moment, but joint moment. Okay, so I want to set formula so that I can save time. I don't need to calculate or repeat the process, the calculation again and again. That is why I choose to use Excel. Okay, so it is negative to represent joint moment. So it is BA plus BC, BA plus BC, okay, times with distribution factor. And for distribution factor, I will put $sign to log, okay, that position. Okay. So that why I need to log that position of the distribution factor, because later when I copy and paste the formula, so the computer will still use the distribution factor. Okay, the value that one, because I have logged that one. Okay, so this one I reduced to 3 decimal places. So again, it is negative. Okay, for joint moment, it is 0 plus, okay, times with distribution factor. Okay, I put $sign. to log that one. Okay, I only log the distribution factor, not the moment. Okay, and then for join C, we have CB and CD. We have CB and CD. So it is total between 72 plus 0. Okay, plus 0 times with distribution factor 0.5, and I log that one. Okay. Okay, reduce this. Repeat again. Okay, doesn't matter. So again, it is 72 plus 0 times distribution factor J3. So I log this one. Okay, so we get this. Okay, there's no moment to distribute anymore. So the next step after distribution is called as carryover. We need to carry over the moment using the carryover factor. There are two carryover factor. One is 0.5 for far and fixed and internal support. Far and fixed and internal support or rigid internal rigid joint like this. Okay, rigid joint. And we have the factor of 0 for end pin. Okay, for end pin. So for this case, we use all 0.5 because we have only end fixed, no end pin, and internal is also we need to use 0.5. And whenever we carry the value, we have to carry the value to opposite joint. Opposite joint means that from B, we have to carry the value to A, we need to carry to B. B, we need to carry to A, we need to carry to C. Okay, same goes to C. C, we need to carry to B, we need to carry to D. D, we need to carry to C. Okay, so we divide by 2 because it is 0.5. This one divide by 2. B carry to A, B carry to C is this one times 0.5. Okay. And we have C, we carry to B, divide by 2. Okay, again. Okay. This one divide by 2. Okay. So we have this. And CD means we have to carry to D. C, we have to carry to D. So this is, okay, divide by 2. This is what we actually need to do in carryover level. Okay, so this is the two things that we actually do in the table. We distribute moment and we carry over the moment. When we distribute moment, we have to distribute join moment, and then we have to distribute moment. So we have to carry over the moment. So after that, we need to repeat again, distribution, carry over. Okay, repeat again. Okay, so what I will do right now is to copy and paste. Okay, so this is the second cycle. Okay, third cycle, fourth cycle. Okay, I will continue to copy and paste until I can see that the moment, okay, in the table, Okay, the value reach 0.00, 0.0, 0.0. Okay, 0.0. Okay, and we can also repeat another one. So it is, remember to stop at distribution. Okay, never stop at carryover. Stop at distribution. The last one must be distribution. So I need to delete this. Okay, so this is the table. This is the table. So this is the table. Okay, this is the table. And then this is actually M naught. This is M naught. Table number 1, we produce M naught. Okay, remember FEM is the first n member n moment. Okay, we have to total the moment in the table start from the first member n moment, which is FEM. Okay, so we total this using, okay, summation, this summation. So we get, okay, all has 6 n moment because A and D both are fixed n. Okay, so this is actually table. Okay, the table. Okay, this is actually table number 1. In table number 1, we get M naught as the n moment and not as n moment. Okay, as n moment. Okay, we only want up to 3 decimal places. Okay, so these are actually, okay, this is n moment for table number 1, so this is actually under step number, okay, step number 2. So in step number 2, okay, summary of the procedure, we have done K and DF in the table, and K and DF will be used in both table 1 and table number 2. Okay, and then we have analyzed, okay, non-sway frame. We have table number 1. Just now I have actually calculated, okay, the end moment due to external loading only, where FEM we calculate from W, which is subjected along member BC. Okay, so we have we have actually calculated this FEM due to external loading, and then we have done distribution table. Okay, so using M naught, we have to calculate R. Using M naught, we have to calculate R. And this R will be calculating using static equilibrium. Using static equilibrium by referring to this diagram. So in this step, we have to analyze this using what we call as shear equation. Okay, step 3 C. Okay, we will analyze restraining force using number 1 shear equation. Okay, shear equation, because why we choose shear? Okay, why we choose shear equation? So when we analyze frame, our focus is column. Okay, when we analyze frame, our focus is column, because beam, in this case, beam displacement in beam has no effect, because displacement in beam is 0. So we focus on because displacement also displacement in column move horizontally. So we focus on the horizontal movement. We focus on the horizontal reaction. So shear, the word shear we use here representing column, representing column where the delta is perpendicular with the column. Column is vertical. Column is vertical member. 90 degree. Okay, 90 degree with column is delta. Okay, is horizontal. Horizontal. This shear equation also reflect the delta. The delta. Okay, shear and delta. Okay, so why we have to use shear? Because of horizontal, it relate with delta. The delta is horizontal. The shear for this column is also horizontal, and R, the restraining force, we need to use R. Okay, we need to use shear equation in order to calculate R, because our focus now is to calculate what is actually R value. Okay, using shear equation for column. Shear equation for column, okay, is in horizontal direction. Displacement is in horizontal direction. Side sway is in horizontal direction in this case. So why we need to have shear equation? Because we want to calculate R, and we can only calculate R by using shear equation. So what we need to do is we have to write equation one equation by using the diagram shown right now, the diagram. So we have to write shear equation. Okay, shear equation, what is the meaning of shear equation? It relate with horizontal, all horizontal forces in the diagram. Relate with all horizontal forces in the diagram, including horizontal reaction at support A and at support D. Okay, so we have 200 kilonewton. Okay, and we have AX. Okay, wait. So will be based on this actually. Fx is equal to 0. Okay, and the direction positive is in this direction. Okay, so we have to write like this. 200 plus AX minus DX minus R. This is equal to 0. This is equal to 0. Okay, this is equal to 0. So now we rearrange this, we get R. Okay, R is equal to 200. Okay, R is equal to 200 plus AX minus DX. Okay, R is equal to 200 plus AX minus DX. So this is actually the, okay, okay, this is the formula to calculate the equation. This is the equation to calculate R. Okay, to calculate R. So in this equation, okay, we have two unknown. We have unknown AX, we have unknown DX. And AX and this AX and DX can be determined using what we call as column analysis. Okay, it is column. Okay, number 2, it is column analysis. It is column analysis. It is column analysis to calculate AX and DX. Okay, so we have to consider only column, because in this case beam, okay, beam is not actually affect the calculation. Okay, because there's no vertical deflection. Okay, in this case, whenever frame has two vertical column, okay, two vertical column, so beam got no effect at all, unless we have inclined column, then only beam we need to consider the delta. So in this case, there is no vertical delta which come from beam. So we just need to analyze AX and DX using column analysis. So for column analysis, we will analyze column AB and column CD separately. Okay, to identify AX, we will analyze column AB by taking moment at B is equal to 0. Then we will get AX value. Okay, and to calculate dx value, we have to analyze column CD by taking moment at C. So we will get dx value. So it is actually like this. Okay, so this is the column. Okay, this is column AB. So at A we have AX. We have AX. We have AX. Okay, this is actually AX. This is AX. Okay, and we have the moment actually. Moment at A, at NA is 20.454. 20.454. 2454. It is the moment 20.454. Okay, and at NB we have 40.949. 40.949. 40.949. It is also positive. And it is 7 meter. Okay, so at A, the vertical reaction, we get any effect will okay, so I just put the value which in the equation, to calculate AX. Okay, the value will contribute to the label will contribute to the value. Okay, AX, in order to calculate AX, okay, the moment at A, the moment at B, we get from table MAB, MBA, and I don't put AY here because by taking moment at B, so there's no effect from AX. Okay, there's no effect from AX, and there's no effect from 200 as well. Okay, from 200 as well, because we take moment at B. So this is only the value that will contribute to the AX value. Okay, so using static equilibrium by taking moment at B. Taking moment at B, which is equal to 0. So we have 40.949 plus 20.454, okay, minus 7ax, and this is equal to 0. So ax is actually equal to 40.949 plus 20.454 divided by 7. Divide by 7. So we get, okay, this. Okay, so it is 40.949. It is 40.949 plus 20.454 divided by 7. Okay, so AX is equal to 8.77772. Okay, 8772. So it is 8772 kilo Newton. Okay, 8772 kilo Newton. Okay, this is how we analyze AX. So we will do the same for DX. Okay, for DX we have, okay, it is actually the same thing. Okay. Okay, but for member CD, the length of the member is 5 meter. Okay, DX is in opposite direction. Okay, this is the DX direction. Okay, we refer to this diagram. Okay, because we write the shear equation based on this diagram, so we have to refer to this one. Okay, and check back the moment at NC and moment at ND. For member CD, it is negative, 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 negative. So it is negative and negative. Okay, negative, negative. So the value is, okay, wait, this is C, this is C, this is D, this is C, this is D. Okay, the value is 5776. 5776. This is 5776 and 25.36. 25.36. 25.36. So this is DD. This is DX. DX. Okay, so by taking moment at C, which is equal to 0, so this we get negative 50.776 minus 25.36 plus 5dx. This is equal to 0. So we get 50 point, sorry, dx first. So this is dx, which is equivalent to 50.776 plus 25.36 divide by 5. Okay, divide by 5. So this is equal to, this is 50.776 plus 25.36. 25.36, okay, divide by 5. Okay, so it is 15.227. 15.227. It is 15.22227 kilo Newton. Okay, so we have AX and DX. AX is 8.722 and DX is 15.227. Okay, 227. So this AX and DX we substitute into R. Okay, we substitute into R. R is, okay, we have R is 200 plus AX minus DX. Okay, so it is equal to 200 plus AX is 8772. 8772 minus 15.227. So this is equal to, okay, this is equal to 200 plus 8.772 minus 15.227. And this is equal to 193.545. 193.545. 193.545 kilo Newton. So this is R value. This is R. Okay, this is R value. This is R value. So now we have actually get R value. So we finish until step 2C. We finish until this step. Okay, we finish until this step. So R is now, okay, determined. Okay, R is now determined. So actually step number 2 for table number 1, it is quite straightforward, where FEM we calculate based on external loading W, and then the value we put into the table and we distribute the moment and we get the end moment in the table. We label as M naught, and from M naught we analyze free body diagram. Okay, we write shear equation, and we shear equation, we get R, formula of R, we get the equation to calculate R. So in the equation we have two unknown AX and DX that we can get from column analysis. So we analyze column AB, we analyze column CD using static equilibrium. Okay, and we get R value. Okay, so this is only the half of the process, because after this we have to move to step, the next procedure, which is 3. Okay, 3 is side sway frame. Side sway frame, the table number 2. So this one, okay, this one I will continue in the next video. Okay, the sides waveframe, table number 2. This question, table number 2, sides waveframe, I will continue in my next video, series number 3. Okay, so okay, actually this video, uh, okay, I have to stop now because now is 1 hour video already. Okay, I will continue in the next video. Okay, to continue table number 2, to continue M prime, to continue R prime, and to finish this analysis. Okay, thank you very much. Thank you for watching. Assalamualaikum warahmatullahi wabarakatuh.